I'm Mark Cavanaugh for Cavi Coaches, and today I'm going to coach you up by letting you in on the kinematics review that I did with my students via Zoom. So we are going to look at some of these problems, and as I said, I have a list of problems that we're going to go through. So we're going to go through the first couple. I'm going to skip number 1, and we're going to go to 2, 3, 4, and 5. So it's important that you understand how to read a velocity time graph. So I picked a couple that have velocity time graphs. So the question for number 2, you're given these two velocity time graphs for particle A and particle B. And it asks which particle is furthest from the origin at t equals 2 seconds. So the origin is just where they started. So it tells us that at the start, they're at x equals 0, at time equals 0. So the origin, they're both starting at a position of 0. So if we're looking at 2 seconds, we're looking at the entirety of the trip. And to find which one's furthest, we have to find the area underneath the velocity time graph to find the displacement. So we can see that this one's moving at 10 meters per second for 1 second. So we find that area, and that's going to give us an area of 10. But then it turns around and heads back the opposite way at 10 meters per second for another second. So what that means is it moved positive 10 meters, then it moved negative 10 meters. So it ends up right back where it started. So it's at 0 after 2 seconds. And this one never changes direction. It's always moving in the positive direction. So we can see that this one has, even though the area is smaller than either of these two areas, it never turned around and headed back towards the origin. So particle B is the one that's going to be further away from the origin after 2 seconds. All right, questions about that? So that one, we're just comparing the areas underneath the curve. All right, so we're going to look at using the same two graphs. Number 3, which particle moves with a constant non-zero acceleration? So moving with a constant non-zero acceleration means that I have the constant non-zero acceleration means that a velocity time graph, non-zero means that it has to have some sort of slope to it. And constant means that if it's a constant acceleration, that graph has to be some form of a line. So I can see that this has a constant acceleration of 0, but it says specifically non-zero acceleration. And it also says constant. Well, this one's accelerating, but the slope of this graph is changing. So that is not a constant acceleration. So in this case, it'd be neither A nor B, because neither one of them show the non-zero constant acceleration. Questions about that one? Everybody's good with that? All right, so number 4, which particle is in its initial position at t equals 2 seconds? Well, we proved that with the previous number 2. That area is equal to that area. So a positive area equal to a negative area means that it's just turned around and come back, and it ends up back at its starting position. So particle A went 10 meters in the positive direction, turned around, came back 10 meters in the opposite direction. All right. Questions on any one of those 3 questions? All right, so looking at number 5. Number 5, so we have this graph is showing the velocity versus time graph for something moving in a straight line. At what time after t equals 0 does the object again pass through its initial position? So this object, in order for it to pass through its initial position, we know that it has to change direction. So looking at this part of the graph, we can see that it's always moving in the negative direction because it's drawn below from 0 to 1 second. So that means it has displaced whatever that area is, 1/2 of -1 times 1. So it's going to be 0.5. So it's -0.5 if you think in terms of a number line, -0.5 from where it started. So where is it going to have a similar type area? Well, somewhere like there maybe a little bit further over here has the same amount of area. So I don't know exactly, but if I look at my answers, between 1 and 2 seconds is going to be about the same area. That's when it's going to pass through its original starting position, is when it gets between 1 and 2 seconds. All right, so remember, it has to cross over the time axis to change direction in order for it to pass through its initial starting position again. All right, questions on that one, number 5. All right, so we're good so far? All right, the next one I have is number 19. All right, so number 19 is referring to this graph where we have car X is that horizontal line, car Y is the sloped line, and it's giving us information for 40 seconds. So it's asking us at time t equals 0, car X is traveling with the same speed, so car X has a constant speed, and car Y, which is just starting to move, or passes car Y, which is just starting to move. So if you think about a real world situation, what's going on here is, let's say you're sitting at a red light, and a car that is approaching that red light is moving at a constant speed. The moment it turns green, you start moving the moment they pass you. So that's what's going on in this situation. So number 19 asks, which of the following is true at time t equals 20 seconds? So we're looking right here, 20 seconds. So car Y is behind car X. So if I'm thinking about behind, I'm talking about positions. So if I want to look and see which car covered more position in the first 20 seconds, I'm just going to compare the areas. So I'm going to look at this area for car X, and I'm going to look at this area that I'm shading in blue for car Y. And I can see that car X definitely has a greater area, which means it has a greater position, which means car Y is definitely not caught up to car X, it's behind, okay? So the key here is you have to remember this is a velocity time graph, not a position time graph. So make sure on the test on Thursday, you're making sure that you pay attention and answer the question for the graph that's being asked, and don't assume the graph. Make sure that you are paying attention exactly which graph it is. So let's go through. B says car Y is passing car X. Well, that would mean that they're in the same position. If they're not in the same position, then they can't be passing. Car Y is in front of car X. Well, we just proved car Y was behind it. Both cars have the same acceleration. So if we're looking at a velocity time graph, we know that the slope is the acceleration. So the slope of car X is 0. The slope of car Y is some positive value, so they don't have the same acceleration. And car X is accelerating faster than car Y. Well, car X doesn't have an acceleration. Its acceleration is 0 with its 0 slope. So no, car Y is accelerating faster. So it in fact is car Y is behind car X, as we proved by looking at the areas. All right, questions on that one? All right, number 20 is the next one that goes along with this. So from the entire time, 0 to 40 seconds, the areas under both curves are equal. Therefore, which of the following is true at time t equals 40 seconds? So we pretty much have the exact same answer choices as we had in number 19. So it's telling us that the areas are equal. So what I have to interpret is that I know that the areas represent the total displacement from the beginning. So if at that point car Y and car X are in the exact same position, well, we know that A can't be true, that car Y is behind car X, so that one's out. Car Y is passing car X. Well, if we look at the graph, we can see at 40 seconds, at that point, car Y is moving faster than car X. So if they're in the same position, we know that that means car Y is moving faster, so car Y would be passing car X. So this is true, but let's look at the rest of them just to make sure. Car Y is in front of car X. Well, if they have the same displacement, it can't be in front. The areas are the same, so that means they're in the same location. So car Y hasn't yet passed car X. It's in the process of passing car X. And then both cars have the same acceleration. Well, we know the slopes aren't the same. Car X is accelerating faster. We know that's not true based on what we talked about with number 19. All right, questions on number 20? Everybody's good? All right. Next one I have is number 21. So which of the following pairs of graphs shows the distance traveled versus time and the speed versus time for all objects uniformly accelerated from rest? All right. So when we know that starting from rest, we know our speed versus time graph has to start from 0, which all 5 of these graphs all start from 0. Uniformly accelerated means that the acceleration is constant, which means that the speed versus time graph has to be aligned. So I can see that for B, that's out because this is a curve and needs to be aligned. For C, again, it's a curve, so that's out. And then for D, I also have a curve, so that one's out. So I'm pretty much looking between A and B. So what I need to do is see, okay, I know that this is showing speeding up. Now I need to look at my position time graph or my distance time graph and make sure that that's showing what I needed to do. So I'm going to draw tangent lines on my curve. And I can see that this graph shows that the tangent lines are getting flatter, which means that the speed is decreasing. These tangent lines for answer choice E, the slope is increasing. And because it's telling us that something that is uniformly accelerated from rest, well, this one it doesn't start from rest because it has a positive slope to begin with, which means it's moving. So A's out, which leaves us with answer choice E. Questions on 21? Everybody's good with 21? All right. After this one, we're going to be skipping around. So let's look at 22. So 22, an object released from rest at time t equals 0 slides down a frictionless incline, a distance of 1 meter. During the first second, the distance traveled by the object during the time interval from t equals 1 second to t equals 2 seconds is, so in this situation, you could absolutely use a velocity, or sorry, the kinematic equations. It's going to take you longer to do that. So what I'm going to do is I'm going to look at a velocity time graph. So what it tells me in the question is that it's released from rest, slides down a frictionless incline, a distance of 1 meter during 1 second. And now what it's asking me is during the time interval 1 to 2 seconds, how far does it travel? So if I go back to my velocity time graph, I know that if something is sliding down an incline, it's just going to speed up at a constant rate because the incline is level, so that means it's going to be a constant acceleration. So if in 1 second it slides a distance of 1, so I know that what that tells me is that this area is going to be 1 meter. And what it's asking me now is what happens in this interval of time right here. So in that interval of time, what I'm going to do is I'm going to compare this interval of time to what I had to begin with, this 1 second. And I can definitely see, just eyeballing and looking at the area, that the distance, that area is much bigger than the first one. So I can come back over here and say, okay, I know 1 meter's out because it travels further than 1 meter. Just looking at the area, I can see that this area here is definitely bigger than this area here. So what am I going to do? I'm going to take a look at this area. I'm going to break that into a triangle. And then here I've got a rectangle. I'm going to break that into 2 more triangles. Well, now what I see is that all 3 of these triangles are equal to that triangle. So if in 1 second it traveled 1 meter, then from 1 to 2 seconds, it's going to travel 1 meter plus 1 meter plus 1 meter. So that's going to give me a total distance of 3 meters that it travels from 1 to 2 seconds. So that's the key, is it's only asking from this time interval from 1 to 2, not from the beginning all the way through to 2 seconds. So you have to pay attention to the wording of the question. All right. Questions on 22. So like I said, for this problem, you could use a kinematic equation. It's going to take a lot longer to set up than just drawing that velocity time graph to see that this area here is 3 times greater than the first one. Go ahead, Charlotte.
So how did you know that those 3 triangles were for sure equal to the first one? Like, because I know it looks like they are, but how did you know for sure?
All right, so the base is going to be equal, right? And the height is going to be equal to this triangle, this first triangle, right? So if this base and this height are the same, when I cut that rectangle in half, it's going to make 2 congruent triangles to that.
Okay.
And as this slope increases, I know that this height and the base are going to be the same as this triangle as well. So I end up making 3 congruent triangles to the first one. Does that make sense?
Yes, thank you.
Okay. All right, that's a very good question. Don't ever use the whole, oh, it looks the same, because a lot of times it'll say pictures are not drawn to scale, but we drew this one. So we know that when we drew it, we know the base are the same, the heights are the same. So the base here and the height's going to be the same because the slope of the line is the same. Very good question. Other questions? All right, so let's clear that out. And that. And now we're going to start jumping around after 22. So the next one I have is 34. All right, so 34 is giving us this velocity time graph, and it's asking for the graph that corresponds as a position time graph along with this velocity time graph. So you're given the velocity time graph, and we want to know which corresponding displacement, x as a function of time, looks best with this. So the first thing we have to do is interpret what's going on in our velocity time graph. So I look at my graph and I can see that because it is always above the time axis, it never drops below. That means it is always moving in the same direction. It never changes direction. The only way it's going to change direction is if that velocity goes from positive values to negative values. And the smallest values I have are 0. It never drops below the time axis. So that means my velocities are always positive. So that means it's always moving up. My position time graph is always going to be moving up as time moves onward. So I can see that this one turns around and comes back down, so it can't be A. This one does the same thing, turns around and comes back, so it can't be B. All right, so now what we want to do is we want to look at the remaining answer choices we have, C, D, and E, and make sure that it represents what we're looking for. So this line right here signifies that the object is speeding up for some increment of time. Then we have a horizontal line, which tells us that it speeds up to a constant speed, and then the velocity decreases, which means that now the velocity has gone back to 0. So an example of this would be you're sitting at a red light, the light turns green, You speed up, you go a constant speed, you get to the next light, it turns red, you slow to a stop. So there's my situation. So what I need for my position time graph is I need the slopes of tangent lines to increase, then I need a linear portion of the graph, and then I need the slopes of my tangent lines to decrease. So if I look at C, I can draw tangent lines, and I can see right off the bat, from the first tangent line to the second one, it gets flatter. I need it to get steeper, so it can't be C. So if I look at D, I've got a horizontal tangent line, which is good because I've got a 0 velocity to begin with. Then it gets steeper, and then here in this increment, looks like it remains pretty linear, and then my tangent lines flatten out after that. So it shows speeding up to a constant speed and then slowing back down. So this is most likely my answer choice, but I'm going to go look at E first of all. So E looks like it pretty much has a curve almost all the way through. Maybe this part is linear, but then the tangent lines start to level out, and maybe that part's linear again. But that's just showing constant speed slowing down to another constant speed. So that's not what we have. We have speeding up to a constant speed and then slowing down. So in fact, my answer choice of D is correct. Questions on 34? Everybody's good with 34? All right. So that concludes velocity time graphs and how to read them and convert them from velocity time to position time, or read them by finding slopes to find acceleration or areas to find displacement. All right, so number 16 is the next one, going back. So I've got to organize these by topic, which is why I'm jumping around. Actually, it's not 16, it's 17. So this graph is what we want to look at, and this question goes along with it. So 17 says the graph above represents position, x versus time, for an object being acted on by a constant force. The average speed during the interval between 1 and 2 seconds is most nearly. So between 1 and 2 seconds, when we're talking about average speed, the average speed, if I draw tangent lines on this curve, those tangent lines represent instantaneous speed. So we can see that this curve got steeper, but that's not what it's asking us about. It's asking us about the average speed. So the average speed is simply going to be, if I take these 2 points and connect them with a line. So the average speed now is just going to be the slope of that line that I drew, because when we're talking about average speed, we know that we have a displacement versus time graph. So again, you have to pay attention to the type of graph that's given to you and not make assumptions. Just look and make sure you're applying the correct principles for the correct graph. So average speed is just the slope between 2 points. It's asking for 1 and 2 seconds, so I draw a line, and I'm going to find the slope of that line. So my rise goes from 2 to 8, and then it runs 1. So 2 to 8 is going to be a rise of 6 meters over 1 second. So that means that my average velocity is going to be 6 meters per second, which would be answer choice D. All right, questions? Everybody good with that one? All right, so there's also another average velocity equation that we have to go over that could be potentially helpful in situations. And that is, let's say that I had this tangent line slope and this tangent line slope, and it asked me to find the average velocity. And it just told me the velocity at 1 second, the velocity at 2 seconds. What I can do is I can take the final velocity, add it to the initial velocity, and divide by 2. Just taking the simple average of 2 velocities would help me find the average velocity between those 2 points. So let's say, for argument's sake, that we are looking at this position time graph, And let's say we wanted to find the average velocity between 0 and 2 seconds. Now again, we could just draw this line right here and draw that line to represent the average velocity. But we can also find the average velocity simply by, or actually any one of these values as long as we have two of them. But we know from the beginning that the initial velocity is 0 because this slope is 0. So that means my initial velocity is going to be 0. So if I was asked, given the average velocity, could we find the final velocity? The answer is yes, because it starts from rest. So that means that twice the average velocity is going to give us the final velocity, with the initial velocity being 0. All right, questions about that? So this is a piece of information that may not be helpful for the test on Thursday, but it could be helpful moving forward beyond that. And since we're talking about average velocity, I wanted to add that in right here. All right, any questions? All right, moving along. All right, number 56. All right, so 56, a bird is flying in a straight line initially at 10 meters per second. It uniformly increases its speed to 15 meters per second while covering a distance of 25 meters. What is the magnitude of the acceleration of the bird? So this is an instance where we could try to draw a velocity time graph, but the problem is we don't have time. So I can't draw my velocity time graph because I only have the vertical axis, and it doesn't give me an amount of time that it takes for that to increase its speed. And it's asking for acceleration. So I have too many unknowns to use a velocity time graph. So what we're going to do is we're going to use our kinematic equations. So I'm going to list my 6 variables. And I'm going to tell you, listing the variables that are in your, in the 6 formulas, if you're racking your brain trying to figure out which equation to do and you're running short on time, this method may seem like it's going to take forever, but it's actually going to help you go faster. So if we go back to the problem, we got a bird flying initially at 10 meters per second, increases its speed to 15 meters per second, and covers a distance of 25 meters. And what we want to know is, what is the acceleration? All right, so information we know it starts at 10 meters per second, increases its speed to 15 meters per second. Then we know that it traveled a distance of 25 meters, which means I need the difference between x and x naught to be 25. The easiest way to make the difference 25 is make initial 0 and the final 25. I could make the initial 25 and the final 50, which is a difference of 25 still, but it's just easiest to make the initial position 0. And then the question is asking for the acceleration, which means, remember, of these kinematic variables, when you read through a question, when you're trying to figure out an equation to use, you're going to be missing one of these 3, either the final position, the final velocity, or the time. And what I mean by missing is you have it, or you don't have it, and you don't need it at all in order to solve the question. So I don't have anything written next to t, so that means I don't need it. And because it's the third of my 3 variables that I could be missing, that means I'm going to use the third kinematic equation on my formula sheet. So I find the third kinematic equation on my formula sheet. Speaking of which, make sure you have your formula sheets printed out if you haven't done so already. I'm not printing out a copy for you, and if you don't have it printed out, you're not going to be able to use the formula sheet, and I want you to have the formula sheet. So please, please, please print those formula sheets out. So the third kinematic equation is the final velocity squared equals the initial velocity squared plus 2 times the acceleration times final position minus initial position. And what we're looking for is acceleration. So remember, if this is a multiple choice question, solve that value any way you want. If this is a free response question, you need to work through the steps to solve for the variable you're looking for first before you plug any numbers in. So I'm solving for A. So I'm going to subtract Vx naught, and then I'm going to divide by 2, and then I'm going to divide by x minus x naught, and that is equal to my acceleration. So now I'm ready to solve I've solved for acceleration. Now I can plug some numbers in. So my final velocity was 15 meters per second, and that quantity squared, minus 10 meters per second, and that quantity squared, divided by 2 times x minus x naught. Well, x minus x naught is 25 meters. So I'm going to solve this. 15 squared is 225. 10 squared is 100, so that's going to give me 125 meters squared over seconds squared on the top. 2 times 25 is 50 meters on the bottom. One of those cancel out, leaving me with the unit of meters per second squared, which is a unit for acceleration, which is what I'm looking for. 125 divided by 50 is going to give me 2.5 meters per second squared. And my answer is going to be answer choice B. All right. Questions on that one using kinematic equations? All right, so we're good. All right, let me clear all this out. And the next one I have is number 67. So I keep telling you that in case you're following along at home if you have this open. All right, so a stone is thrown straight downward with a speed of 20 meters per second from the top of a tall building. If the stone strikes the ground 3 seconds later, about how tall is the building? Assume air resistance is negligible. All right, so in this case, it tells us a time. It does not tell us a final velocity. So there and again, it's going to take an extra added step to draw a velocity time graph to figure this out. So I'm just going to go ahead and skip and use my kinematic equations. So listing my variables again. And then I'm going to read through the problem, and I'm going to figure out what I know. So the initial speed is downward at 20 meters per second. It hits the ground 3 seconds later. So that's all the information that I have. So I'm going to assume for this case that downward is positive. Just because it doesn't change direction, it's going to make it easier for me to solve for what I'm looking for. So I'm going to say that it moves initially at a velocity of 20 meters per second. It takes 3 seconds to hit the ground. Now, because it is thrown downward, as soon as it leaves that person's hand, it is now in free fall. So once it's in free fall, we know the acceleration, because the acceleration is going to be 9.8 or about 10 meters per second squared. And all the multiple choice are usually calculated using the answer choices using 10. That's why it says about how tall is the building, because they're using 10. If you use 9.8, it's going to round to the correct answer. Okay? So you can use 10 on the multiple choice, 10 on the free response. The only time I will tell you you need to use 9.8 is when we're doing labs. So in this case, you can use 10 since that's the way the exam is going to be calibrated. And then I'm going to say that throwing it downward from a initial height, I'm just going to call it, since I'm saying downward's positive, I'm going to just say that initial height is 0. And then it's moving downward in the positive direction. So what I'm looking for is how tall is the building? Well, I just need to know how far the rock was thrown, how far it traveled. So I'm looking for that final x, which means of my 3 variables that I'm looking for, or that I would be missing, I'm missing my final velocity. That is the second of the 2 variables that could be missing, so that means I'm going to use the second kinematic equation. So my second kinematic equation is x is equal to x naught plus vx naught t plus 1/2 at squared. And the best thing about this equation is it's already solved for what I'm looking for. So now I can just go ahead and start plugging numbers in. So x is equal, x naught is 0, so I don't need to write that. Vx naught is 20 meters per second times t, which is 3 seconds. So seconds are going to cancel out, leaving with meters, which is a good unit, is a unit I need for position, plus 1/2 of 10 meters per second squared times 3 seconds, and that quantity squared. So those seconds squared are going to cancel out with those seconds squared, leaving me with the unit of meters again. So 20 times 3, that's 60 meters, plus 1/2 of 10 is 5. 3 squared is 9. 5 times 9 is 45 meters. So that means my overall height of the building is 105 meters. So we come over here and we see, yep, that's one of our answer choices. So it's answer choice D. So the key to that question is remembering as soon as it leaves the person's hand, it's in free fall, which tells me that that value is going to be my acceleration. If you use 9.8, you would just get something a little bit less than 45, but you can see your answer choices, nothing else is close to 105. So you might get 102 if you use 9.8 or something close to that, and it's going to be much closer to 105 than anything else. So using 9.8 or 10 is going to give you the correct answer. So it doesn't matter which. The answers are calibrated in 10, so you can use 10, and you see that we got this exact same answer using 10. All right, questions on that one?
Yeah, I have 2 quick questions. One is kind of general. Are calculators active on the multiple choice?
The whole thing. Calculators are active on the entire AP Physics 1 exam. Yes.
And on this specific problem, so the final velocity of x, we don't know. I was thinking it would be 0, but would that be incorrect because it wouldn't be 0?
Good question. Very good question. So that final velocity represents the velocity that it would hit the ground with.
Oh, okay.
So it's not after it hits the ground, because as soon as it hits the ground, now we've got a different type of motion. This acceleration is no longer valid once it hits the ground. So if you're using that as the final velocity, the velocity that it hits the ground with would become the initial velocity. So,
all right. So that's why we don't know the final velocity.
That's why we don't know the final velocity, because it's how fast it's hitting the ground.
Okay, thank you.
Okay. All right, other questions? Everybody's good with that one? All right, so let me clear the screen. All right, so that was 67. Next one, looking at 68. All right, so we have a coyote. It can run at a speed of 20 meters per second. A prairie dog, poor prairie dog, can only run 5.5 meters per second. So the prairie dog is 45 meters in front of the coyote. What is the maximum time it has to reach its hole without being caught? All right, so we did this problem. This was the Sue driving in the tunnel question from the textbook, and wanted to see if she ends up colliding with the truck, which we found out, yes, in fact, she did. And we also did this as our lab practicum, where we had 2 cars moving the opposite direction. So what we did for both of those is we found position as a function of time, and then we either set those equations equal to each other, or we graphed them and found the intersection. All right, so we know we're going to write our position functions. So what we know is I'm going to go ahead and write out my 6 variables. So this is for the coyote. And remember, I'm writing a function of position as a function of time. So I'm not going to know those, but I need those values in order to write my equation. So what I know is, well, the coyote's running at a constant speed, so acceleration is 0. I know that the initial velocity and final velocity are going to be the same because he's running at a constant 20 meters per second. All right, but I know that I need position in time. The first equation doesn't have position. The third equation doesn't have time, so that leaves me with my second equation. So I'm going to use this equation to write my position as a function of time. And because the acceleration is 0, I don't need that part of my equation. And for the coyote, we know the coyote has an initial position of 0 because it tells us that the prairie dog is 45 meters in front of it. So we're going to assume that coyote starts at position 0, the prairie dog is 45 meters ahead. So that means x naught is 0. So that I can use an equation of x is equal to vx naught times t. Well, here's my vx naught. So my function for the coyote, so we'll put a little c here for coyote, x of c for the coyote. There's my function for the coyote. So now we're going to list the same variables for the prairie dog. Well, the prairie dog started 45 meters in front, and it's only running 5.5 meters per second. So that means its final velocity is also 5.5 meters per second. And this speed is constant, so that means the acceleration is 0. So again, we're going to use that same kinematic equation. This time, the x naught is not 0 because we've got a position of 45. So the final position of the prairie dog is going to equal 45 meters plus the 5.5 meters per second times t. All right, and to refresh our memories, it asks what is the maximum time. So what is the maximum time it has to reach the hole without being caught? So now we can take these two equations, and if we know that the maximum time is going to be when their positions are equal, is when the coyote is going to catch up to the prairie dog. So I can set xc equal to xp, the position of the coyote equal to the position of the prairie dog. So I end up with 20 meters per second times t is equal to 45 meters plus 5.5 meters per second times t. So now I can just solve that equation. So I subtract 5.5 t, and I'm going to get 14.5 meters per second times t is equal to 45. And then divide both sides by 14.5. So t is going to be 45 meters divided by 14.5 meters per second. So meters are going to cancel out, leaving me with 1 over 1 over seconds, which is a unit of seconds. And 45 divided by 14.5, that one I can't do in my head. We end up with prairie dog's got about 3.1 seconds to reach its nest. So 3.1 seconds, my answer choice is B. All right, now I'm going to tell you, if you have a question like that, it's probably going to be more of a multiple or a free response question, not a multiple choice, because that took a lot longer than 1.8 minutes, which is what you get on the exam, 1.8 minutes per question, which is what you'll get on my test. So that would probably be more of a, you're going to sketch a graph, you're going to write a function, or you're going to set equations equal to each other. So that's more of a free response type question. That's going to take a little bit more time. So if you're sitting there thinking, oh my gosh, this question is going to take forever, it's not going to be a multiple choice type question on the AP exam or my test. All right, questions on the prairie dog question? Everybody's good with that one? It's now the third time we've seen that type of question. So I'm going to go ahead and clear these out. All right, next question I have is number 73. So if you're following along at home, number 73. All right, so we have two identical bowling balls, A and B. So A and B, each dropped from rest from the top of a tall tower. Ball A is dropped 1 second before ball B is dropped, but both balls fall for the same time before ball A strikes the ground. Air resistance can be considered negligible during the fall after ball B is dropped before ball A strikes the ground. Which of the following is true? So the distance between the two decreases. So the best way to look at this is think about a velocity time graph. So we have a velocity versus time graph, and A is dropped, so it's going to speed up. B is stationary for 1 second, and then is dropped. So what I can do is just kind of look along this graph and kind of look, okay, here's 2 seconds, here's 3 seconds, there's 4 seconds. And if I kind of just eyeball what's going on with these areas, I can see that A's area, so this is A and this is B, A's area is increasing quicker than B's area. So A's is getting bigger and bigger and bigger, more so than B's area. So that means A's distance is getting further and further and further from B. So the distance between the two balls is not going to decrease, it's going to actually increase. So the velocity of ball A increases with respect to ball B. So what this means is that if the velocity is going to increase with respect to ball B, what that means is they would have to have different acceleration values. But the moment they're dropped, they're in free fall. So we know that both of them have the same acceleration. So after 1 second, B would be moving at 10 meters per second, which means that A is moving at 20 meters per second. Then B is going to be moving at 3 seconds, it's going to be 20, and A's is going to be 30. So they're always going to be 10 meters per second off from each other. So A's velocity is not increasing with respect to B, it's always going to be 10 meters per second faster because it was dropped 1 second before. Then the velocity of ball A decreases with respect to ball B. Well, we just answered that. They're always going to be the same velocity difference between them, so it can't be C. The distance between the two balls remains constant. Well, we just proved with the area that the areas of A is increasing faster than B's, so that means the distance for A is going to get increasingly larger than B's. And the distance increases between the two, so that means my answer choice is E, sorry. So A is going to be, at every point along the line, it's going to be moving faster than B. So that means it's going to be covering more distance each succeeding second. So that means the distance as they drop are going to increase, and the ball A will end up further away than it was initially when B was dropped. Questions on 73? Everybody's good with 73? All right, I have one more that I'm going to go over, and then I will open it up to you if you have questions. So that is number 78. So 78, starting from rest, an object 1 falls for 4 seconds, and then object 2 falls freely for 8 seconds. Compared to object 1, object 2 falls, and our answer choices are half as far, twice as far, 3 times as far, 4 times as far, etc. So again, we've got objects in free fall. So again, we can look at a velocity time graph. And that tells us, so let's say this is object 1 that fell for 4 seconds, and then object 2 fell for 8 seconds. And the question is asking us, starting from rest, object 1 or object 2 falls compared to object 1. So here, we're starting from 0. So I can see that object 1 fell whatever this distance is here. So this is similar to the problem that we had a little bit earlier, except for the wording's a little bit different. So let me extend my line a little bit. So I can look, this is where, so object 1 fell for 4 seconds, object 2 fell for 8 seconds. So again, I can see that this is 4 seconds here, that's 4 seconds, so the bases are the same. Whatever this height is going to be the same as this height and this height. So I can put that into 3 triangles. I don't like that symbol. So let's call this, it fell a height h. And then that means each of these triangles is h. But now we have to look at the wording of the question. The wording of the question says from rest. So we're looking at both of them from time 0. So if object 1 fell a distance of h, that means object 2 fell 1, 2, 3, 4 h's. So that means it's going to go 4 times as far in those, that double the amount of time. All right, questions on that one? And again, you could use kinematic equations. I just feel the velocity time graph gives you a good visual representation of what's going on with the distance that is being covered by those. So I'd like to use the velocity time graph instead of kinematic equations. Plus, I think it's a lot quicker. All right, any questions on 78? All right, that is all I had planned for review. Do you guys have any questions for me about anything in general? Go ahead, Ben.
Access the recording for this.
I'm going to post it in Google Classroom. It's recording right now, so as soon as I'm done, I'll click stop, and then I'll save it, and then I'll post the link in Google Classroom.
Okay, thank you. And also, I came in kind of late, so you may have already answered this, but for the test, is it just going to be multiple choice and FRQs, or are there going to be like graphs and motion maps too?
So there's going to be 10 multiple choice, and on the AP exam, you get 90 minutes to do 50 multiple choice, which equates to 1.8 minutes per question. So I'm going to give you 10 multiple choice questions, and you'll get 18 minutes to do the multiple choice. And then once we're, just like the AP exam, once we're done with multiple choice, we're the multiple choice you can't go back to. You're done with the multiple choice. Then I'm going to give you 2 short free response questions, and you'll get 26 minutes because each short free response you get 13 minutes to do. So I'm going to give you 26 minutes to do the free response questions. And sort of like last year, if you took any AP classes last year in the COVID world we were in and it was shortened AP exams, you're going to have that full 26 minutes to work on the AP or the free response questions. And then I'll give you the amount of time that you need to take pictures of it and upload it to Google Classroom, I think is where I have it for your exam tomorrow when I post it. Okay, does that answer your question?
Yes, thank you.
So in the free response questions, you could be asked to do anything that you just said, drawing graphs, writing equations, using equations, written explanations, things like that that you would be asked to do on the free response. And the multiple choice, you'd just be asked to interpret those graphs and just kind of pick things that go along with that. All right. Other questions? Very good question.
About how many parts are the short FRQs? Like 3?
Short FRQs usually are 3 parts, A, B, and C. But some of those could have shorter subparts, like B could have part 1 and part 2. So it could be 4 parts, but it might be something that's just a quick analysis and you read the question, and from the question, you can answer it pretty quickly. Okay? All right, other questions?
Sorry, for this kinematics review that we went over, are all of those problems pertinent to this chapter? So like any of those could be used as chapters that could
So there are questions in there. So I teach it a little bit different than a lot of textbooks are written and a lot of teachers teach it, is we just do one-dimensional, so straight line kinematics. So any problem in that set of problems that says something is launched at an angle or is launched horizontally, we have not covered the two-dimensional kinematics yet, which we will get to a little bit later on. So if you come across one of those, just know that anything that has a parabolic shape, so any problem where it says you have something launched at some angle theta at some initial velocity, or it might be launched horizontally at some initial velocity, those problems don't do. So if it gives you a picture of something that has a trajectory that looks like this, you don't have to do those either, okay?
Thank you. And then is there an answer key posted to that or not?
Yeah, if you scroll all the way down to the bottom, the answers for all the multiple choice with an explanation and the scoring guides for the free response questions are there as well.
Okay, thank you.
All right, other questions?
Can you go, oh, sorry.
Sorry, you can go.
Okay. Can you go over the free response question we have in class? Like the
Which
rocket?
one? The rocket one?
Yeah.
So I believe I got that one from here. Sorry if it's making you dizzy. Oh, for the quiz that I gave you, this is question 1 from the quiz. So if you wanted to look at the quiz that I posted, this is question 1, and this one is question 2. So you can scroll down and find those years, 1993 B1, and find the scoring rubric for that. And then the other one is 1982 B2 or B1. So you can find those, just scroll down. That's the questions I used for the quiz. All right, there it is. All right, so what specific question do you have about that, Anna?
It's part C.
Which one?
C.
The speed? So determine the speed of the rocket after 2 seconds. All right, so we know in the question it tells us it has an acceleration of 30 meters per second squared for 2 seconds, and it's being launched upward. So that means it's not moving. At this point, it's not moving. So if I list out all my variables, if I want to use a kinematic equation, I know I showed you in class how to use a velocity time graph for this, so I'm going to show you the kinematic equation way here. So I know it starts at a position of 0 because it's on the ground. The initial velocity is 0 because it hasn't launched yet. It has a acceleration for 2 seconds of 30 meters per second squared. So, and what I'm looking for is the speed. So I don't know the first variable, which means I'm going to use the first equation. So Vx is equal to Vx naught plus AXT. I know Vx naught is 0, so I simply just have to multiply acceleration times time. So 30 meters per second squared, decimal there, times 2 seconds. So one of those seconds cancels out with that one. So I end up with meters per second. So my units check out, and I end up with 60 meters per second for the speed. Okay? All right, other questions?
Is the test going to be virtual or will we have a physical copy?
You're not going to have a physical copy this time. So the multiple choice is going to be on one site, and the free response are going to be on Google Classroom.
Okay.
So, which I'll talk to you guys about that when we're in class. So this time it's going to be, everything's going to be online and paperless. So you'll have to provide your own graph paper and your own notebook paper for writing answers down, or just showing scrap work for the multiple choice. All right.
Okay.
Other questions?
Wait, for the FRQs, can we do like with the AP exams last year where we draw and take pictures to submit?
So what we're going to do is you're going to work it out on paper. As soon as that 26 minutes is up, then everybody will take the pictures, and then you'll take the pictures, upload it, delete it from your phone, and then we'll move on and then you'll turn it in through Google Classroom. Okay. All right, other questions?
So how do you know whether it's preferable to use like a velocity time graph or the kinematic equations?
So that's a very good question. My suggestion is if you think about using the kinematic equations, and you know these three things right here, that is the key that say I can make a velocity time graph, because I know the initial velocity, I know the final velocity, and I know how much time it took for it to go, so I can sketch a velocity time graph. So remember, in physics 1, it's algebra based, so acceleration is generally going to be constant if you're drawing a velocity time graph, which means velocity time graphs in this class are all going to be some sort of positive slope, negative slope, or horizontal line. Okay, so there's not going to be any curves that you would have to draw. So if you don't know one of those three, then I suggest using the kinematic equations instead of a velocity time graph.
Okay, thank you.
All right, other questions? All right, if there are no more questions, then I'm going to sign off, and then I will wait till this saves and then post it, and it'll be in Google Classroom probably within a half an hour. So I hope you all enjoy your half day tomorrow, enjoy your assembly, and I will see all of you on Thursday. I will have tutorial Thursday morning, and then I'm available for one-on-one drop-ins tomorrow from 10 to 11:30. So if you want to just drop in and ask questions after the club fair tomorrow, you're more than welcome to do that. Okay? All right. Then I'm going to sign off. Everybody have a great day and even better tomorrow.
Thank you, Mr. Kavanaugh.
Thank you too.
Thank you.
If you found this video helpful, don't forget to click the like button down below and subscribe to my channel, Cavi Coaches, and follow me on Instagram and Twitter at